It's day 3 of the advent of compiler optimizations, and today we're going to continue looking at ads, but we're going to actually look at some compiler optimizations today as opposed to just some code generation bits and pieces. Let me show you what I mean. So here we have basically the same code that we had yesterday, except that today I'm compiling with Clang and I'm targeting the ARM v8 architecture, which is a little bit less quirky than the x86. It still has its fun, so we'll look at some of those examples as we go on through this series. This is the 64-bit ARM variant, and so W0 and W1 are the 32-bit versions of the first two registers, and here we can see the compiler has generated a relatively straightforward add W0, W1, W0, which says W0, the return value, is equal to W1 plus W0, and the first two arguments are passed in W0 and W1. So it's kind of switched them around, but it doesn't matter in this instance. So unlike the x86, the ARM can in fact add and put the result in a different register. So we can add together the two inputs and put them in the right place for the output in one instruction, which is great. Let's try some different add routines. Let's try something a little bit more surprising. So I'm going to type in unsigned add v2. I'm using unsigned here because, and I can't type, unsigned y. So let's do something like x plus equals y. So we're going to update x and then we're going to return x. What we end up with is exactly the same. The compiler has seen through the difference in the code and realized it doesn't need a local variable, doesn't need to update the local variable, it can just return it. Perhaps that's not too surprising. Makes sense, right? The compiler does this kind of optimization. Again, we're on 01 here. Let's try an even more strange way of adding stuff together. So let's do add v3, and we're going to have, in fact, let me just steal this. Add v3 is there. And now I'm going to say while x minus minus y plus plus return y. And even though I've said keep looping decrementing x until x is equal to 0, and every time round increment y and then return y, the compiler has worked out that that loop is effectively just adding two numbers together. So the compiler is pretty darn smart. I wouldn't recommend that you write code like this, but it's interesting to see that the compiler can see through these things and still generate optimal code. The last one is a little bit more complicated, so I'm going to paste it in from my notes. This one is a recursive function. The recursive function says if y is equal to 0, return x. That's our sort of base case where we say if the y parameter is 0, we return x. Otherwise, we return the result of adding ourselves with x plus 1 and y minus 1. And eventually one of those two values will end up being 0, and then we return the other one having added it, incremented it the right number of times, which is not a very straightforward way of phrasing it. Now you can see over here on the right hand side, the compiler has in fact generated a loop, but we're only on 01. 01 is kind of fine for almost every use case. It's a pretty pragmatic choice for faster compilations, but it's not unreasonable to deploy 02 or even 03 code. So if we put on 02, the compiler sees through even this recursive function and realizes that it too can be replaced by an add instruction. Now again, you shouldn't be writing code that looks anything like this, but if you do, the compiler can often determine what the correct instruction is, even though you've gone out of your way to make it more difficult. I really wouldn't recommend that you write code like this. It's a terrible idea, but after sort of inlining and template expansion and other parts of code or dealing with other people's code, it's not entirely impossible that you end up with something a little bit like this. We'll talk more about some of the inlining tricks and things that the compiler does later in the series, but rest assured that however your code ends up, the compiler is looking hard to try and optimize it as best it can.